You can have a cup of coffee and snacks. Yeah, free. Oh, that's not mine. Hello, hello. Can you guys hear me? All right. So welcome to EECS277, data-centric computer architecture. So today, well, before we start, one thing I always like is I like to know each of you, and I like to know your New Year resolution. So who you are?
Below this year, and I want to sell my car this year.
You want to what?
I want to sell my car.
You want to sell your car? Okay, what kind of car is that?
It's a 2008 Mercedes SLK 280.
What's the feature of that? How much are you asking for?
I'm asking about 11,000, 90,000 miles.
Okay, 90,000 miles for 11,000. Given that's a Mercedes, is that a good deal?
It's probably not.
It's probably not. Okay, okay. If you are interested about having a car, what's your name again?
Below this year.
Okay, contact him.
My name is Albert, and I'm trying to pay off my car.
You are going to pay off your car? Are you on mortgage for that?
Yeah, I'm financing.
Okay, you are financing it.
My name is Jesus, and my resolution is to drink less soda.
Drink less soda. Okay, that's a very, very, very concrete one.
My name is Cameron. Want to find a job.
You want to find a job? Okay.
My name is Karan. I would also like to find a job.
You also like to find a job. Do you want to find a job? Not yet?
Not yet.
Okay.
Yeah, but I'm planning to buy a car.
You are trying to buy a car. Okay, contact him.
I'm David. I'm trying to work on my first paper.
Okay. Okay, getting your first paper out. That's a very realistic one as well. Well, maybe you will have one from this class.
I'm Charles, and my resolution is to be nice with everyone.
Be nice to everyone. So are you used to be not good, not nice to everyone? He is mean?
He's very mean.
Okay, how long have you been knowing each other for?
1 quarter.
1 quarter, and you already feel like he's very mean?
Nice.
Okay, what's your name?
My name is Jordan, and I want to fix the windshield to my car.
Okay, everyone has a car problem.
Hello, my name is Annie, and I want to go to Vegas and see the Magic Mike show.
Okay, Las Vegas. Why not sing the Sapphire? The Sapphire, there's something called Sapphire. How many?
The Magic Mike show is like muscle man on the stage, and the dance and.
Yeah, no, I'm thinking about like in Las Vegas, they recently built a Sapphire, right? How many of you saw this on TikTok, YouTube, or whatever social media? They have a lot of cool stuff outside. Check that out.
Okay.
I'm Rabin Silva, and I'm planning to jog every day this year.
Okay.
My name is Kana, and I want to be less stressed.
Less stressed. Okay, so this is probably not a bad class to keep you stressful, to be honest. Well, we will figure that out later.
I'm Joseph Rodriguez, and I don't have a resolution.
You don't have resolutions, meaning that your resolution is that I just want to keep having like good life like this, right?
My name is David, and I want to get better at drawing.
Better at drawing.
I still draw stick figures, so I need to fix that.
Okay.
Yeah, My name is Song Yu. I want to learn more in the new year and be distinctive.
Okay, that's a very ambitious one.
Hello, my name is Dan Hua. I want to find a research group and do some research.
Okay,
My name is Fred. I want to learn some skating.
some
Skating.
skating.
Yeah.
Ice skating or just in general the roast?
Anything that can slide and skate. That should be fine.
On the road, on the snow, on the water.
Doesn't matter.
Doesn't matter. Okay, you can take a surf class. I probably won't be a good teacher, but I know how to surf.
My name is Zhongwei, and I want to find a job this year.
Okay.
I'm Ingrid and I also want to
Okay, everyone wants to find a job. Yep. Okay. So, so great to see you all today. So, you know, like as you can feel, we are trying to create a very different class from whatever you ever took before. Like this is probably well. So one of the review I got the last time I taught this class was some people put the comment, "This is the most delicious class that I ever take in my life." So this is probably, yeah, right. And this year, so in the past, I only have snacks, but not drink. But this time I get coffee because I realized this is 2 p.m., right? And this is right after lunch. This is the time that everybody feels drowsy. So why don't we just have a cup of coffee, right? So if you haven't get one here. Okay, so but before we start the topic, I want to make sure that we are on the same page in a way that everybody know what kind of a world that we are living. So I want you to remind yourself, I want you to grab a few people around you to talk about your understanding in the modern world that how does a computer process and store data right now? Go. You don't remember anything. This is water, right? Or half and half. This is, oh, 2% milk. We also have sugar and this if you want. Yeah, we have a few more cups if you need. Next time I will get some water. Yeah, I know some people don't drink coffee. Or maybe tea. It cannot be even lower. Wait, they should have. Oh boy. Oops. All right, what do you guys recall? Anything you want to share with the group, with the crowd here, with the class? What do you learn? Jesus, what do you have in mind? You are not too far away from my course, I remember. Just last quarter, and you got an A plus, right? Do you?
An A, I think.
An A? Okay, yeah, that's good enough. What do you remember from my class?
So I don't the process data.
Oh, okay.
there's a
When you
process
start, I
data.
was thinking about like I don't remember anything. I was.
So there process data, you use a CPU
Mm-hmm.
to store
We
data.
have the CPU.
To store data, there's SRAM, DRAM,
Mm.
storage,
Mm-hmm.
registers even.
Mm-hmm.
Yeah, that's about it.
Okay. Anything to add? So we have CPU, we have memory, we have register, we have SRAM, DRAM as the memory, we have storage. What else? What else are in your mind?
The Van Neumann architecture is primarily used.
Von Neumann architecture. Okay, remind all of us what is von Neumann architecture. A lot of you, I know you have heard about that a lot, right? But what is that?
You're always having you have some form of memory, you have some processor,
Uh-huh.
and there's one I think storage. Is it storage, memory, processor?
Uh-huh.
And how they basically interact with each other in order to store information.
Uh-huh. Okay, so that's the von Neumann architecture. John von Neumann, von Neumann architecture, you have processor, you have memory, right? So typically when you want to execute a program, right? The program, first of all, right, when you compile the program, when you store the program, right, you basically put it in a storage. And then when you want to run it, right, it has to be presented in a memory first, and then your processor fetch instructions from the memory, and then based on what instruction is, we execute the program accordingly, right? So why von Neumann architecture is so popular, and it's actually the dominating architecture in a modern world. The reason is just so simple in a way that, the beauty of von Neumann architecture is that whatever you give in a memory, the processor will just run it. And what does that mean is that, like the Sphere, right? So today, if I load a program, want a Sphere to show some emoji, right? That's what it will do, right? But if today, like a lot of you might saw in a Christmas Eve, it becomes a moon or something, right? Then if I load a different program, different context into the computer controls the Sphere, then it will do a thing that's totally different, right? So that's the beauty of von Neumann architecture is that nothing in the hardware that you need to change once you build a computer. The only thing that you need to do is change the content in the memory, and the computer can potentially perform completely different. So I don't know, well, talking about Las Vegas, right? Well, in the past, right, like the slot machines that you have, when I was a really, really young child, right? Well, when I was a really, really young child, am I supposed to go to Las Vegas to play with the slot machine? Okay, here's the thing, right? So the thing is that, okay, the old slot machine, they really have a bar, and the bar is like some kind of mechanical stuff, and it really controls like a microcontroller, and the microcontroller would control some kind of well, later on they have the LED display, but in the good old days they have some kind of plastics, and you seem to know a lot, right? And it really rolls, right? And the mechanic thing would determine when are we going to stop, right? To be honest, I think that's even more fair than what it is now. But what we are doing right now is that, well, we just put a personal computer on it, and we have a very nice monitor behind the slot machine, and it will pretend it's showing those scores, right? And then you put a random number generator, although most of us know it's not random, right? And if you're lucky, you will see 3 sevens, but most of the time you won't see, right? So that's and sometimes, right, if you put a different program inside that slot machine, it will give you different types of slots. Like instead of 3, you can probably have 5, right? And some of the more advanced one, you can even choose what kind of game I want to play with. So that's totally different, right? So in the past, if it's all mechanic, there's nothing you can change once you build that slot machine. But nowadays, all you need to do is put a flash drive in there, change the program. The slot machine could be advanced to most recent content that you want it to be. So that's the beauty of von Neumann architecture. So that's the hardware part. So if you have such a hardware, what your program would look like? Can you tell me like what's the typical process when you process data in your program? What's the typical process look like? What's the very first thing you do? What's the second thing you do? What's the third thing you do? What's the last thing you do? Or maybe more. Any idea? Okay. Okay, that's actually, okay, so you have data stored in big little endian, and then how are you going to deal with them in your program? So I'm talking about if I'm writing a program on a computer. Okay, so we say, right, the von Neumann architecture, if you put a different program into memory, the computer will perform differently, right? But right now the question is that if I want to process data, what's the typical formation of a program? Like, what are the typical things that your program would do? Load the data, and then some operation, and store it back again. Okay, so when you load the data, can you directly use it? Right, so let's take a look of a typical program, right? So let's say, oops. Okay. What? I didn't change my password this year. Okay, here we go. Yet. Okay, so here's a typical program, right? So this is a GMN example. So what happened here is that typically, right, you would have some kind of code, allocate a data structure in memory, right? And then, well, this is, and then probably something like fopen, right? And then through the fopen, you probably use scanf to read your data, parse your data, and put them in a data structure, right? Okay with that? Are you guys all okay with that? Right? And then finally, right, so this is probably a very giant part in the very beginning of your program. Basically, you load the data and try to put them in a data structure. And then what is this data structure used for is that we are going to use the data structure as the input of some kind of, for the input of your algorithm, right? Like for this program, it's the C+ GMN, which is the GMN function that's optimized for the CPU architecture. And then finally, you print out the result and store it back, right? So that's a typical process, right? So let me see. Okay, so that's a typical process of a program. So you can see, right, what do we typically do? Every program that you wrote is pretty much like this, right? So first of all, I have data stored on storage in some format, but most of the time, the format may not be exactly what I want. The data structure in a data structure that what I exactly want for my algorithm. So it turns out from the source data, you have to make them data structures, right? So for example, if the data that you store is going to be a tensor data structure, then you have to realign them or assign the values you got as tensors. And then you use your algorithm to run on those inputs and generate outputs and store them or present them to the user. So that's the typical process of running the program. And typically, you use secondary storage to store your source data. You store your data structure in a memory as well. And you use your processor or GPUs or whatever hardware you can think of to run this algorithm and then put the result in a DRAM, right? So that's a typical process of our program in modern days, right? So now answer me a question. In von Neumann architecture, or in a way we program, what's the center of your computer architecture? What's the center of the computer architecture that we have now? what kind of design are we centralized? Computation. Okay, so it's a computation centric. And can you be more specific? Which component are actually in the center of the computer architecture? CPU, right? So look at the program, right? So to be honest, who sent a command to read the source data? Who creates that command? Where that command is issued from? The CPU program that you are running, right? And if you look at the code, right, we also have the code that creates the data structure, right? So it turns out that the data structure is also created on by using CPU program. And then for the algorithm, you may be able to run it on GPU. But if you look at, okay, so let's continue looking at this example, right? So right now, I'm showing this example as, so this is the example that you use the CPU GMN to run the code. But today, well, if I want to use GPU, right? So if I want to use GPU, let me see what, do I have a version of the GPU program here? Kublas SGMN. Okay, tensor core GMN. Okay, so maybe I can show you this. So demo intro matrix small Kublas. Is this Kublas? Simple tensor core GMN. What is that? Simple tensor core GMN, DGMN. This is Kublas GMN, right? So this is the version of the code that I use to run the CPU, the GPU version. So if you look at the GPU code, right? Although we tell you it's a GPU program. However, let's look at the GPU program, what it looks like. First of all, it still have a main function. Where does the main function start? On the CPU still, right? And then we use malloc to allocate the data structure on the main memory, not on the GPU yet. And then we read the data again on the CPU, right? And later on, okay, we try to set the mode of Kublas to like here example is the default map, and then we use the CPU program to communicate with the GPU to allocate memory space on the GPU, right? But again, this command is still issued from your CPU program. And then later on, malloc, that's also on the CPU and the main memory, and main copy from the main memory to GPU, right? So your CPU is still involved here. And finally, okay, here is this single line, Kublas SGMN. So in here, that's the only place we transfer the control of the program, or in fact, it's the CPU program delegate GPU, give authorized GPU to run this SGMN function to perform your matrix multiplication, right? So turns out, even though it's the GPU program, right, you are still using a CPU-centric model to run your application, right? So turns out it's kind of interesting, right? CPU is playing such a very, very big role in your program. So turns out for this particular matrix multiplication program, let me show you this demo, right? So if I have, so right now I have two metrics. One is the data A, the other is the data B, right? And let's see, right? So how much time that I need to run is about like 59 milliseconds total, right? So if you only count the mathematical kernel, the GFLOPS here of the CPU is 291, which is, if you know the performance, so now let's try the Kublas version, right? You will see it takes about, if you see the total time, it's actually longer than a CPU program for 4 seconds, right? But if you look at the amount of time we spend in a GPU kernel, it's only about 12 milliseconds. And the GFLOPS of the GPU is actually not that bad. It's 1.3 terabytes, teraflops, right? So it does have higher performance when running this GPU code. However, for the rest part, because we are heavily rely on the CPU to do everything, and in fact, before you can delegate the function to the GPU, you need to do some preparation, and that preparation is actually taking more time than your actual kernel, right? So that's actually one of the issue with our current GPU architecture, our current architecture. So here's the thing: although most of the time we live with the fact that we have computer volume computer like the right hand side part of the plus the DRAM part of the basic elements, right? And when we try to add more stuff in there, we never thought about change the CPU-centric architecture, but we just add more stuff as peripherals in the system. So turns out what end up with is that, okay, first of all, right, in volume architecture, CPU memory, they are tightly coupled. So in our modern computer architecture, we do give the CPU memory privilege access to each other in a way that most of the time your DRAM is directly connected with your CPU with a very wide memory bus with a dedicated memory controller. For example, here we have DDR4, and some of your computer might have DDR5. But no matter what kind of controller it is, it's a memory controller dedicated for your main memory, and it typically have like tens of gigabytes of bandwidth. So exclusive between the CPU and the DRAM. And for the rest part of the world in your computer, they all connected to this PCIe root complex. And this PCIe root complex connects your hard disk drive, it also have a dedicated bus connecting to the memory controller. But other than that, right, everyone is, every other peripheral has to connect with the PCIe root complex before they can talk to others. So actually in your computer, all the peripherals are connecting in a star topology that the center is the PCIe root complex. And where the PCIe root complex is actually your CPU. So if you look at how we put all components within a computer, again, this is a CPU-centric architecture for sure, right? So we are living in a world that we have CPU-centric architecture. So is this an efficient computation model? Talk to people around you. Is this an efficient computation model? Why or why not? No.
So then, what? I think so, right? So instead of having to go through memory storage, reports processor, so actually it would be processor sends get to the memory, the memory has to tell you, okay, new actions like that, and it takes the space that makes it like makes that different. Our main limiting factor is the CPU, right? Because that's true. Yeah, good question. So like ISAs, right? We were ISAs to sure that no matter what experience, you essentially have we were on campus for a year.
All right, so is it an efficient computing model? I kind of like misled you in the example that I gave, but so it's welcoming to give me counter examples. Why do you think it's an efficient architecture? So, but let me know what you feel. Albert.
I think it's an inefficient model.
Oh, why?
Because a lot of our ways we have to access, we always have to go to the processor first.
Mm-hmm.
And if we could maybe skip the processor and be able to access maybe like from a GPU to memory straight away, we might be able to skip the time that takes to go in between or the overhead.
Okay, so it's from a traffic perspective, right? So it's like, okay, you have a hub for everything, right? So not sure how many of you remember the story last year during the holiday season for Southwest, right? So during the pandemic, so I'm a very frequent flyer of Southwest Airlines because I was based in San Diego, and Southwest actually control 40% of the traffic from San Diego, so it's easy for me to fly Southwest anywhere. And Southwest has been changing a little bit. So in the previous CEO, when they built the Southwest airline, they are actually using the model that Albert was talking about. So they have a lot of direct flight, point-to-point flight to small cities or secondary cities. So like from San Diego, I can fly to El Paso. How many of you know where El Paso is? Okay, some of you know, some of you doesn't know, right? But it's by no means a big city, to be honest, right? But we have flights like that. And from Ontario, we can fly to a few different places as well with Southwest. So that was the model that they tried to build. But at some point, I figured out that Southwest has changing themselves. So right now, if I want to fly to somewhere further, somewhere past the Middle West, I always have to fly through a city called Denver. And the reason is because during the pandemic period of time, they tried to save the cost, and they figure out that because the declining of the passengers, number of passengers, if I have too many point-to-point flight, I'm actually having a lot of loading flight instead of flights with high loading, right? So it turns out that they try to put all the traffic into Denver and have connecting flight to Denver from everywhere. But what happened last year is, well, 2 years ago, not last year, is that there was a heavy snowstorm in Denver, right? And then turns out that a lot of flights are jammed in a Denver airport, and plus they have the very, very old software system, so their old scheduling get failed, even though those flights, they are totally okay. The pilots, the flight attendees, they are all there, but no one can fly because of that issue, right? So that's, as you said, right? If we could have direct flight from one point to another point without going to Denver, things are easier, right? But, and another thing, right? Like, okay, so for people living in Riverside, we are kind of sad in a way that we are inland, right? So every time when we want to go somewhere in the Southern California, we have to go through like Los Angeles, right? How many of you love Los Angeles? Not me, for sure, right? The traffic there is so terrible, right? So can you imagine a life like, okay, everyone has to go through Los Angeles downtown, right? That's pretty much why Los Angeles traffic is so bad, right? You see so many highways, they interchange with each other in Los Angeles downtown, right? So people saying that Los Angeles traffic is so bad for a reason, because they try to put all the traffic, put all the network, put Los Angeles downtown as the center of the traffic network. So it's congesting all day. So sometimes, like I have a friend from San Diego asking me like, what's the best time of going to Los Angeles? And I was telling him like, okay, I was asking him, what time are you thinking about? And he say, probably 8 a.m. And I told my friend, no, that's too late. Right? Because after 8 a.m. until like 8 p.m., the traffic is always bad. All right, so that's one reason. It's an inefficient computation model. What else? What else? All agree it's an inefficient computation model. But now my question is that if it's inefficient, why do we build a computer in this way in the very beginning? Have you ever thought about that? Is it really bad? Why do we build computer in this way? It's easier to? Okay, so in the very beginning, right, it's called computer because we just wanted to compute, right? So in the very beginning, its main function is compute, right? In fact, okay, so this is a paper published in 1998. So probably not too far away. A lot of you, that's probably the time a lot of you were born, right? Or how many of you were like after millennium? Okay, you were not born at that time. Okay, awesome. So before you were born, right? This is the typical, this is the workload that we are running. As you can see, like compress, right? You still run a lot of program, compress, decompress. There's JPEG, there's MPG, right? You still use those data formats. And Tomcat, not sure how many of you remember that, but it's a, I think it's a P2P software or something, right? And if you look at the time that we spend in memory, it's actually not a lot, right? If you look at that, oh well, so this is a, yeah, because this is an old paper, so don't expect it to have colorful graph. But if you look at the amount of time we spend in memory, right, they are not the majority, right? The black part is called useful because that's actually the time that the CPU can use, right? Can run that, right? So you can see, right? Even in 1998, it sounds like not too far away, right? At that time, memory is still not the majority of your execution time. So you can go back to the very, very old word. If computation is the main problem that I want to address, then why bother optimize my computer for memory, for data storage, right? And the thing is that this computer is working, right? Typically, we don't change things that are working already. So we just keep adding stuff there, right? That's probably happened to a lot of your car, right? Like if your car is ready to drive, right, you probably won't have a different car, right? Instead, you might have some add-ons to your car, right? Like for example, replace the audio system, make it Bluetooth compatible, support Apple CarPlay, right? Does your car support Apple CarPlay? Oh no, I'm not going to buy it, right? Upgrade it, right? So typically, right, you don't change the car. So and also, right, like if you look at the car that we have right now, even Tesla, its structure, our exterior structure is pretty much the same as a gasoline-based car. Hybrid car is still leverage the same design, right? But why? Because the original design works well, right? I don't find a compelling reason to change the user behavior, right? So that's why the CPU-centric architecture keep going on, and all we do later is just keep adding stuff there. But what's the problem? So we have been talking about the PCIe root complex is where we connect all computers, all peripherals. However, how many lanes does PCIe root complex have? So some of you might be questioning sometimes why Intel sells server processors a lot more expensive than conventional processors. And here's the reason. So these two, they are actually the desktop processor that you can purchase from Amazon. So if you look at the number of PCIe lanes that we support in in an Intel desktop CPU is only 20. And for AMD processor, you can get 24, right? So, okay, thinking about that, you only have 24 lanes connecting to other peripherals. And if you look at the speed of the PCIe compared against computing, so this is the GFLOPS of your hardware. And here, typically in PCIe, I should use the number gigabyte per second as a bandwidth instead of the GFLOPS. But here, I change it in a way that I assume that this are computing 32-bit floating point numbers. So this is actually divided by 4. How many 32-bit floating point that PCIe can transfer at that period of time per seconds, right? So even with that, you can see the PCIe bandwidth is actually way lower, orders of magnitude lower than your CPU or, and needless to say, GPUs, right? So it's definitely a bottleneck of your modern architecture. So, so if you look at so it's definitely a bottleneck of the modern architecture. And in fact, remember that, right? So for, okay, here we go. Okay, in fact, in modern architecture, as we mentioned, right, the CPU has 20 lanes in total. And how many lanes do you think your GPU is going to occupy? 8? 80% of that? Okay, so that's around the right number, but typically, right, it's, as you said, 80% and even more. So it's actually like, okay, typically if you get a GPU, it will suggest you to have allocate at least 16 lanes to it, right? So 16 divided 20, oh yeah, that's about 80. Okay, you have a good estimate. So what does that mean? If you have a GPU installed in your system, all the rest can only have 4. And each LAN is only 1 gigabyte per second, right? So all others has to compete with this 4, including where you store your data, which is essentially the source of your data. So that's why data loading could potentially become a bottleneck in this CPU-centric architecture. But as I said, right, I don't know how many of you watched this show before. It's a show in Japan, and I like to watch it. So what they typically do is that I give you a house, and because the family changed their mind, so they want to make the house different, right? So, and what I want to say, another thing, well, not being showing off. So the upper side is actually my old place when I live in Pasadena, and the bottom one is actually my new home in San Diego, which I purchased last year. And can you tell me what's the difference between the new one and the old one, instead of except for the top one is older, the lower one is newer? What's the main difference you can tell from here? A lot more cabinet space. What else? Okay, so a lot more cabinet space because a lot of us like to buy things nowadays, right? So we need more storage. Okay, what else?
There's more permanent structures. So for example, you can't just take out the cabinets.
Okay, a lot of stuff are fixed. What else? Furniture. Okay, I have furniture on the up-hand side. Okay, remove those furnitures. Yeah, because this one is actually taken before I move in.
Oh, there's ceiling lights?
Ceiling lights, okay. That's because right now, all of us are bad in reading. Right? We need to read a lot, so we need the ceiling lights. What else? Uniform design style, more stylish. Okay, so you guys are not architects. If I'm, the bottom one is kitchen, right? So the right-hand side of this bottom one is actually a kitchen. But on the top one, do you see the kitchen at all? So that's the difference. So, you know, yeah. I'm serious. So in interior design, right, the 21st century idea of interior design. So how can you tell this is a new house or an old house? the most significant thing you will figure out is where the kitchen is. So in 21st century, all the interior design are centralized by an idea that kitchen should be the center of a home. Why is that? Because most of the time, okay, to be honest, like tell me how much time you spend in your living room. See, right? So in modern world, people typically don't spend that much amount of time in the living room anymore. But we need to eat, right? Especially this period of time, right? Eating outside is so expensive, right? So we need a kitchen, right? So turns out that the modern world, the design has been changed from the living room centered design to a kitchen centered design. Because we understand the reason why we want a living space is not for watching TV, right? Like most of the time, even though I have a big TV, I still want to watch on my phone, right? Instead of watching on the TV. So right now, the world has been changing in a way that, okay, people like to use the living room just for cooking stuff, eating stuff, rather than spending a lot of time in the living room with others, right? And even though I'm using the living room, right, typically I'm just having party with my friends, right? So that's why I want a kitchen island, right? Because people are still here for eating something, right? So turns out that once you figure out the mission is different, you will have a totally different design. And as I just mentioned, right, in the past, we designed a computer to be CPU-centric because it's a compute-centric design. So now I want to ask you one more question. What will you do differently if you realize the fact that most of the time we are interacting with data, with storage and memory instead of just computing? How are you going to change your computer architecture? How are you going to design the interior of your computer differently? Go.
Most of the time, it's data storage, chip-based data storage, even more pathways. It also could be that if all of each other on it is based in the same. Yeah. That's true. What if something just like you need different instructions for because it's not like you say you give one thing. I think it should go different. Nowadays yeah, but I mean, machine when I don't have the general purpose computer. You have one data center for everything. It's true. I mean, I don't know if it makes that much sense. I mean, it does make sense, right? It's because like you should have a
All right, so architects, how are you going to redesign your computer? If you scratch out all the CPU-centric design and design your computer, how are you going to make it differently? Jesus, any idea?
Increase bandwidth for one.
Increase bandwidth for.
And like maybe also make your storage where the root of the PCIe would be, for example.
Okay, so this is what you think, right? So you want to have a, okay, so we want to have an SSD, right? And you also have a PCIe root complex here.
Yeah.
Okay.
But like that would be connected to everything else.
Okay, so basically, okay, here's the thing, right? You want, okay, saying that we have a GPU. So you probably don't want to have a root complex from what you mentioned here, right? You want to have a point-to-point connection, right? This is CPU, point-to-point. Who else? Maybe TPU, right? NIC, network interface card, right? So you have this, and network interface card can talk to GPU, can talk to TPU, right? It seems like a very complex topology. Okay.
I have a question. I don't know if like this is loud. If the PCIe is on the GPU, then would it still have to take up 16 lanes for 80%?
Okay, so if the PCIe is on the GPU, do we still have to take 16 lanes? Again, it depends, right? Like how intensive do you want, like what's the, okay, so here's the thing. Are you going to build like a 16 lane road in Riverside? No. Are you going to build a 16 lane road in Los Angeles?
That would be nice.
That would be nice, right? So it depends on how heavy the traffic is going through the device, right? So do you think we are going to have a lot of traffic still on the GPU? Yes, right? Because the throughput of GPU is so high. So that's why we need 16 lanes. So you still want to have traffic, well, a lot of the lanes going into the GPU. But now the question is that where this 16 lanes goes to? Storage the only thing. Maybe NIC, right? If some of your data are from the network, right? And don't forget, we have the main memory. That's a faster memory, right? Okay, so if everyone has 16 lanes connecting to GPU, is it going to work?
No.
It's not going to work, right? Because it's very expensive. Okay, what else?
I'm sorry. Oh, what is it?
Network interface card. Yeah. What's CPU? Tensor processing unit. Okay, so yeah, I was about to, yeah, we can talk about that in the next lecture. But TPU is one of the accelerator that Google built for AI ML workloads, and you will read a paper about this in the next lecture. Okay, okay, so looks like the point-to-point idea still have its trouble, right? What else? What else do you have in mind? Increase the frequency of what? Of the memory. So from my architecture class, what do you learn? Is it easy? No, right? Because of what? Because of the power issue, right? So it's not that easy. What else? Decrease the length of the PCIe, but is it good? Like GPU is so hungry for data. Is it a good idea to decrease the length? Depends on the competition. So, okay, so you are saying I can control how many lanes that I want to connect to each different unit, but is it easy to do it in hardware? So in hardware, right, like I cannot say that my motherboard move a few lanes to a certain component easily, right? Because the hardwire nature, right? Okay, so maybe I can give you a hint. What's the reason why we need to move the data around? Why do we have to move data around? In order to compute. But why do I need to move data whenever I need to compute? The processor cannot store a lot. Or the other way around, can a storage compute? Maybe. Okay, so here's the thing, right? Another reason why modern home become more kitchen-centric rather than living room-centric. I don't know how do you spend your life during the pandemic period of time, but to be honest, like how many hours do you stay in your room during the pandemic period of time? All of it. But why can you stay in your room for almost every hour during the pandemic period of time? Because my room has everything I need, right? It has a bed, I can sleep. It has a standing desk, I can work, right? I can also put a small refrigerator with a microwave, then I don't even need to step out. And if I have a bathroom inside, then I'm self-satisfied. And I can pretty much stay in my room for the whole week, maybe the whole month, right? What? Whole pandemic? Probably not, right? You still need to get the grocery. Oh, here's the thing. That's why we have We and Uber Eats, right? Okay, awesome, right? So here's the thing. You have to make your device self-contained. So the reason why you still have to move data around is that we are so restricted in a way that we thought the compute device can only do compute and data storage can only do data storage. But what if I have processors everywhere, right? What if I put a processor on the SSD? So in fact, we are not too far away from it. So here, you can pass it along. This is, well, but remember to return it to me. So this is a prototype data center SSD. And here we have a lot of flash memory chips. And for this one, I believe we have 4 terabytes of storage. And in the center, you see a heat sink, right? So this heat sink, under the heat sink is actually a 16-core processor. So the reason why they have a 16-core processor is because this is a data center SSD. It has 16 lanes connecting to the PCIe root complex. And to support that high bandwidth, you actually need a processor to handle those commands fast enough. And why we need and why they finally end up put a 16-core processor on it is because instead of like manufacturing a microcontroller and using firmware update all the time, why don't we just put a general purpose processor on it? But in fact, that also tells you your storage has a processor on it, right? So you can take a look of it. And in fact, based on that, so this is a product from Samsung, and I got it last year. I haven't got a time to set up. So if some of you are interested about setting it up and use it for something for this, like for your project, that's actually a good vehicle that you can use. So this is a smart SSD. So they have a U2 connector connecting to the, and you can have a converter, make it PCIe. And this SSD is heavier than usual because in addition to the flash memory, it also have an FPGA on it and a microcontroller on it. So you can actually reprogram the FPGA as an accelerator for processing data on the SSD. So we are actually the distinction between compute device and data storage device is actually vague now, vague enough in a way that we can implement the idea of near data processing. So like I said, right, if I have everything in my room, why do I need to step out? So here's the same idea. If my storage device can do a lot of things, I can reduce the chance of having my data going out. And in this way, you are more data-centric in a way, is that I only leverage the compute power, more powerful processor because I need. So it's depending on if the demand of processing data rather than the processor controls everything. So that's a new idea of data-centric control. However, again, should every computer be data-centric? You know the answer. If you took my class before, that this kind of question is always, it depends. But here's the thing. Here's the big thing that I want you to learn from this class is that, but how do I know? What's the right design for those it depends answer, right? So for a lot of you took the final in my class, when I have this kind of question, you always say, well, it depends, right? But to be honest, if you get a degree in master or PhD, the company doesn't want you to just tell me the answer, it depends. I just want you to tell you right now what to do, right? So this is the class that teaches you how to answer what to do. Okay, so the reason why you are here for the first lecture, because you want to know what's going to be in the class. So let's jump into that. So again, typically, when you were born as a human being, you have 3 different basic questions: why, what, and how, right? Like when you are a child, when you are a kid, right, you like to ask a lot of whys to your parents, right? Until a point that your parents realize that, okay, you are asking a question, why am I in the world? How do I get to the world, right? Then your parents stop answering questions because they figure out that, well, there are a lot of things I don't know how to answer. So sometimes in elementary schools, right, teachers don't like to tell you why, because that will make their life miserable, right? So, but that's why we need universities. And in fact, in the past, if you think about what you have learned in university as an undergrad, in high schools, we are trying to tell you what and how most of the time instead of answering why. So in this class, I will try to cover most of the why behind a lot of papers that we are going to read. And we are going to have a project for you to pick one of the idea and maybe implement it as your project. So this class, as you can tell, we are going to ask you to read a few papers before the lecture. And in the past, I was very ambitious in a way that I want a student to come without reading a paper. And I thought I did a good job, but some of the reviews saying that it's still better to ask us to read a paper beforehand. So in the past, there's no such a part that I want you to fill the paper summary, but this time, let's try it. But don't feel the paper summary is overwhelming. I actually don't want you to spend too much time. To be honest, if we have 2 papers, I want you to try to finish the paper summary within 2 hours. And for each paper, I only ask you 2 questions. One is, what's the big research problem that the paper is trying to address? And what does the paper propose to solve the problem? So these are the only 2 questions that I will ask you for each paper. So what I want you to do, and one of the very important skill I want you to know, is that I want you to pick up a paper and within a very short period of time, and you would be able to identify if this paper is relevant to me immediately. So that's one of the skills that I want you to learn, pick up after this class. And that's why we want you to submit this paper summary, which don't feel too stressful about it, because that's just make sure that you at least skim through the paper quickly, right? So, and some of you might be thinking about, I'm just a master's student, why am I reading papers? But in fact, these are some of the emails that I got from good old days, that a lot of people, they do care about do care about papers. They are all from industry, from different companies. So, you know, industry cares. So here's what I expect you would learn after taking these courses. So in this class, we are going to talk about, we are going to teach you 4 different technical perspectives. So one is performance analysis. But this is an advanced version of the CS203 in a way that in CS203, we only talk about MDOS law. We only talk about CPU performance equation. But for this class, we wanted to estimate the maximum potential of a program. And that's something that CPU performance equation won't tell you. And then with that, you can know if I am really designing the most efficient architecture for my application. And also, you can also, based on the performance you measure, you will figure out if I fully utilize the hardware that I have. So that's the part about the performance analysis that I'm going to cover, which is complementary to what you learned in CS203. And also, right, as I said, the current world is living in a CPU-centric architecture. So beyond CPU-centric architecture, what are the options? So I'm going to talk about hardware accelerators, as some of you talk about what is TPU. Don't worry, that's what we are going to talk about. And near data processing, as I told you, how can we embed computing power into memory devices, right? And what are the innovative hardware architecture that we are having? And another thing, which I think is also important, is that only giving you the hardware doesn't make the story, right? So we want to talk about what kind of a new programming model resides on this new architectures and what kind of new programming platforms are we going to have. So for example, since I worked for TF Lite before, a lot of you know, I probably would go through the TF Lite a little bit, and it's a different perspective than using them for AI ML programming. And also we have the new smart SSD, so if you're interested, you can definitely investigate that. And also a demo that I originally want to show, but because of the time, we don't show it, but the way how you represent your data, the way how you store your data actually play a big role in your program performance. So those stuff we are going to cover. And so let me see. Soft skills. A few soft skills that I will teach is that, so again, why am I talking about soft skills? Because end up, a lot of people asking me, why doing a PhD? If I pick a topic, am I going to live with the topic forever? And I want to tell you the answer is no. And what really matters about PhD or grad school is the soft skills that you learn. So this is also a class that is going to equip you with some of the soft skills that you can use for the rest of your life or maybe throughout your PhD or grad study. So I want you to, hopefully after this class, you have the ability to figure out how to identify big problems, big research problems in our community. And as I said, right, how can I just read a paper within a very short period of time and I can pick up the main idea without spending the whole day reading a paper, right? And coming up with new research ideas, that's very important, but only idea is not enough. How can I work in a group and how can I draft a solution to the research problem that I create? So that's another set of skills that I want you to learn. And again, you already feel like this lecture is very different. At least this lecture provide free food, right? So I will try to bring snacks and coffee all the time. So keep everybody awake. So what kind of show, right? Like I like to do peer instruction for CS203, but this class I'm not going to use clickers. Instead, I like to be opera in a way that like you guys are the guests of mine, right? And I like to hear your thoughts, right? So this is the show that we are having. And grading, a lot of you care about this. So we have two sets of grading. So one is the paper summary. So just submit the paper summary on average 1 hour per paper, right? And fill out the form. You will get the 50% of the grade. And some of you were asking about, do we have Piazza? Do we have Canvas? And due to the small of the class, we are not going to have Piazza or Canvas. But some of you might already be aware. If you log into your UCR email, we actually have a Google Space set up. So if you have any question, just ask through the Google Space. And if you are not in there, send me an email, I will add you in. And another half, which I like you to practice, is that we learn a lot of new idea, right? can we turn them into a research project? And a few research ideas that I have in mind. So for example, pick one application you have in mind, and let's try to accelerate it through existing AI ML accelerators. And because that's aligned with my research, so I have an infrastructure for you guys. And intelligent storage devices. So where's my smart SSD? Okay. So like we can actually have some of you try to help me set up that smart SSD because I just got it last year. I don't really get time to get it set up. So that could be a potential project, right? And another thing is that because of the new hardware accelerators we have, so for example, like ray tracing accelerator, tensor cores, there might be some kind of new parallel programming model that's enabled by this kind of hardware. So that's potentially a research project that you can conduct in your class, this class. And this class would be this project. We are welcoming you guys to work in a group, and actually you are more than welcome to work in a group because this class we don't have TAs. It's just me and you, right? So if you work in a group, that's actually better for me, right? So maybe 4 in a group, no more than 4, right? So we provide the infrastructure. We will have a containerized environment, and I will install TensorFlow, TF-Lite, CUDA on it. And the hardware available for you are GPUs, edge GPUs, and the GPU also have ray tracing accelerator. So you got a lot of stuff. And other soft skills that I think you need to learn is how to present. So we will have 2 sets of presentation. One is like the milestone presentation. Just talk about the big problem that you and your group are trying to solve on the 4th week. And on the 10th week, just talk about your current progress, and we are done. Okay, so that's pretty much the class, and this is who I am. I am an associate professor at UC Riverside, and previously I've been working in Google's TensorFlow Lite group, and that's some of the very interesting experience that I had in my life. Prior to that, I'm a PhD student. I was a PhD in UC San Diego, which is not too far away from here, and I'm interested about using AI ML accelerators for a lot of other things. And yeah, so that's about me. So one last thing is that we have the course webpage. So if you want to find all the resources, please go through the course webpage. And if you don't know where the webpage is, you can go to my personal website. I have a link on there. And we also have the recording on my personal YouTube channel. And you should be invited into the Google Space. So that's pretty much the materials we have. And before you leave the classroom, a few things that I want to let you know. First of all, most important thing, find your group at most 4 and discuss your research idea within your group and set out an appointment with me next week so that we can confirm this is a research idea that you are going to work on. And you know, if you like you, right? If you want to publish a paper, right? Think about an idea that can publish a paper, right? And like in your area, like there is a packed deadline in like April 15th. So maybe we can shoot on that, right? And check out our Google Space, not Slack, because I was trying to set up Slack, but you know Slack is too difficult to manage. So it's Google Space, and also check our website. There are 2 papers listed already for the next lecture. Again, spend 2 hours. If it's more than 2 hours, don't spend more than 2 hours on these papers, right? Try to write something. I'm not going to check your paper summary in detail. So don't worry about that. Just make sure that you read those papers in a way and submit your paper summary before the lecture. Other than that, we are done. I will see you in the next lecture.
Suggestions or like institute for the project?
Yeah, so I think something that I try, right? So for example, think about some application. Yeah, so
And like maybe like pick something, would it be okay if we ask you for suggestions for like maybe